I'll now introduce my colleague, Dr. Mervyn Smyth, who is in Belfast, who'll be taking you guys through the concept or the technology aspect of our product. Thank you.
Thank you, Eng, and hello everybody. Yeah, hello from a very, very sunny Belfast today. Belfast is never sunny, but of course, that doesn't take away from us in terms of the work and the development that we're doing here. So Ulster's role is really looking at the technology, the concept, the prototyping of the systems. We're looking at a whole system approach, in that we're looking at how we can integrate, we can hybridize both the provision of solar thermal and solar PV in one unified system. The diagram on the right is a schematic that very simply gives you a good overview of what the technology is about. So the two principal hardware elements are the solar catcher, that's the solar thermal element, and the PV with the battery and balance of system, all tied together through the innovative control system that we'll be developing. If I can start with just giving you an overview of the solar catcher. The solar catcher is not like any other type of distributed type solar water heater or thermosiphonic close coupled solar water heater that is commonly installed perhaps in Botswana. It is an integrated collector storage system developed by Solarform, a spin-out company from the University of Ulster here in Northern Ireland. When I say it's an integrated collector storage system, what I mean is that the collecting element and the storage element are combined in the one unit. Now, this technology has a thermal diode built into it, and that's the special IP or the patented element of the tank. Effectively, think of a big, large thermos flask. The solar energy incident upon the unit is converted into heat and stored as hot water in the unit. And then with the vacuum that surrounds the system, we can retain that heat for a longer period. The other interesting aspect of the technology is the PV panel itself. That was fabricated through a company that hails from Poland and the UK. And they developed a PV panel that is designed for harsher climates. So higher exposure to UV or higher temperatures, or indeed perhaps more regular dust and abrasive action. So in terms of the diagram, what you've got there is a singular unit. It's basically got one solar catcher and one PV. That is what we call our entry unit. This was the unit that we developed. We called it the Solar Fin2Go technology, and it was installed in Jamataka in northeastern Botswana, where field trials are still going on. My colleague will give you a little bit of an overview of that later on as a backdrop to where the technology has come from, and indeed where it's going. But that is the singular entry-level format. The system provides a certain amount of hot water and a certain amount of PV power. But if you needed more power, because of the modular format, you can bolt on 1, 2, 3 extra solar catchers and PVs to ramp up the amount of power and hot water that can be delivered. In terms of the power delivery and the mechanisms that we've built into it, first and foremost, the PV generates the power, which goes through the smart controller, whereby power can be wheeled directly to the household and supply electricity to the appliances, or indeed be put into the battery for storage. Now, what's interesting is that we have built in a number of immersion heaters into the solar catcher, so that if there is any surplus power, i.e. there's no load requirement or no battery top-up requirement, that power can be fed directly into the solar catcher to augment or to top up the hot water in the tank. But also, if the smart controller says so, then that power could be wheeled back out onto the grid if ultimately the grid was suitable to accept any of that power. From the water heating point of view, instead of the water being directly directed into the household, the cold main feed would feed into the solar catcher first of all. Thereby, if the hot water was sufficiently hot enough, it would be fed directly to the end user. Now, at this point, if the water wasn't hot enough, say for example, it was below 30 odd degrees, which is obviously not comfortable for a shower or other type of bathing activities, then the smart controller can wheel power from the battery to provide top up to give an extra small amount of heat other than the surplus heat that I already discussed. There also is the provision for an extra boost. We call this button the Masood button, and that's something that my colleague Masood maybe will talk about later on. But it really means that you can say you don't have enough hot water in the tank, you can take electricity from the battery to give you a 15-minute boost that brings the water up to a temperature warm enough to have a shower. So the hot water can be fed, as I said, directly into the appliances, or a certain percentage of it or all of it can be then fed into the electric geyser that may be in the household. Again, this will offset, reduce the amount of electricity demand needed in terms of heating the water for the household. So this is twofold. A, it's beneficial to the end user, but ultimately, if you think about the bigger picture, it's taking that power load off the grid and therefore giving some sort of benefit to the grid, perhaps from a stability point of view. And again, my colleagues will maybe talk a little bit more about that later. The two other images that you see are just the technology under testing in our solar simulator lab facility. The image in the very center is the solar catcher with the PV with a little electric and line heater and a little electric geyser storage system. Again, we were able to test those within our facility. And then the final image on the left is the rest of the solar system, the balance of system with the batteries, along with a lot of our monitoring equipment and our simulated load equipment.